Let me start with a scheduling update. So scheduling update, my plan is to go over the finite square well today, along with the homework, to review on Tuesday and then give you the test on Wednesday. Does that work? The test from last week, compared to the week before.
Yeah, so how much finite square well stuff will be on the test?
As far as problems, remember, they're, quote, small problems,
Okay.
right? So there's no full-on anything. So it's going to be a piece of something that we do. Well, they will be pieces of things that we do, not any full, complete thing.
Okay.
So, I could, for instance, you were asking about the tanh,
Yeah.
the hyperbolic trig functions. I could have something like that. I could have something, how do you solve a transcendental equation? But you're not going to have the whole 9 yards for anything because it's, who has that time?
Okay.
Not on the test. So Chad asked about a homework problem. Which one was it you wanted to look at? Let theta be the step function, also known as the Heaviside function, as defined below. Show that the derivative is a delta function. So in the global scheme of things, we need to first think about the Heaviside function looks like that, right? It's 0 here and 1 there. So how do we show that that's that the derivative of that is the delta function? Well, there should be 2 things you know about the delta function. What are the 2 things you know about the delta function?
Like what it's equal to at different points, and then also that the integral of it is 1.
Yeah, those are the 2 things. It's equal. What is it equal to at points other than 0? 0. It's equal to 0 everywhere except for where x is equal to 0. Right, so that's, I'm just going to add another page here because this page is full. Page manipulation, insert, let's insert 2 just in case. So we know the delta function equals 0 for x not equal to 0. That was the first thing you said. And then we know that the integral is 1, right? So all we have to do is check and see if the Heaviside function actually fits this. So without even having a mathematical equation, I can look at my graph. What is the slope for everywhere except for x equals 0? 0. So the derivative is 0 for everywhere except x equals 0. So this one here, check. Right, that we didn't even have to do mathematically. I mean, I could have come and I could have said, well, the derivative of 1 is 0 and the derivative of 0 is 0. Right, I could have done it mathematically, but just looking at the graph and thinking about it logically is what I prefer. Now we have the second part, the integral. Well, the integral of the delta function is 1 if we go from minus epsilon to plus epsilon, where epsilon is some small value. Now, if we take the Heaviside function, we know that the integral of the derivative of the Heaviside function with respect to x dx, right, because we're checking to see if this is the delta function. If we take that integral, that's got to be equal to h evaluated from, right, I've done the integral by the fundamental theorem, and I used h. I guess theta is what you're supposed to use for the Heaviside function, right? Yeah, theta. So I used the fundamental theorem of calculus to say that if delta is, well, I'm using d theta dx to see if that's delta. So that's this, but then I just look at my definition of my function. This is going to be theta for x equals epsilon minus theta for x equals minus epsilon. But theta for x is equal to greater than 0 was 1. And theta for, so this one here goes to 1. And theta for x less than 0 was? Those are the two things. Now, if you look at my solution in the, when I post the solutions, it's much longer. But that's all we had to do.
So just to kind of check what we were talking about with the single delta function last Tuesday, you said that the potential energy went down to negative alpha.
I'm checking to see if I had a nice picture of that in my.
Yeah.
I don't remember what I used for the front picture. Nope, I didn't put in something with a nice picture. Okay, so yeah, I just have different pictures here. I had some pictures that I was going to show, but I didn't. So go ahead and ask your question then, and I will.
So technically, like, since at x equals 0, that delta function is saying that it's actually infinity, how do we get then?
Going to minus infinity.
Minus infinity, yeah. Then how do we get to the potential energy? It's just going to negative alpha instead of to negative.
Or actually, no, it's not going to minus infinity. It's we have the alpha there, so the integral of the potential energy is has a value of alpha.
Yeah.
Now I understand what your question is now. You have a delta function that, I think I said it's infinite, right? Because you have an infinite slope, but it has a finite area. And so in that problem, we had I don't know how to answer your question. I don't know how to answer your question because you're right that what we really have is the integral. We can do that integral like we did for the boundary condition.
Right. Yeah.
Right. In that case, it wasn't that the potential energy was minus alpha.
Right.
It's that the integral from one side to the other, which gave us it was the integral of the second derivative in that case. But the integral of a delta function is 1. And so that's when we have minus alpha when we do the integral.
Yeah. So when you graph it, are you just automatically assuming that you're taking the integral of Vx in order to get those?
No, it actually should be a spike that goes down to infinity.
Okay.
Down to minus alpha infinity.
Okay. Yeah.
Whatever that might mean. So I don't have a perfect answer for that. Obviously, the math is sound. We've all done it. And you kind of get lulled to sleep after a few years and forget the good questions like that.
Is that why on this, it just has spikes? It doesn't show the spikes going down to negative alpha? Okay,
let me go to, wait, do I have, oh yeah, that's right, on page 7, right. Well, I just took this from a book, so I can't really.
Okay.
Don't remember. This does give you if you just take off this portion, that's what we had for our picture. Okay, now I have, like I said, 2 things I want to go over, and I gave you all of the notes for the work. so I can go through it a lot quicker and you still can make sense of it. And I know that's not per solution. I will give you a story if you understand how I know that's not the solution. When I was in graduate school, Dr. Marston, for the first time in his life, he used an overhead projector to teach. And so that was from my class. And so he was loving it because he was able to cover so much more. And, we're like, can't keep up. But he was so excited that the next year he had them put in a second overhead projector so he could go from one to the other and go faster. And so the students after me were like, what? How can we do this? You've got to go at some reasonable speed so we can kind of comprehend it. So I understand, but we're short on time. So if you look at my presentation here, it's only 4 pages. It's only 4 pages with all of the work then on the other one. So here's a picture to compare the infinite well and the finite well. So you see the pictures here. It's pretty clear what the difference is. The infinite well is walls that go up forever, and the wave functions come down to 0, and they're not shown here, but it's just 0 outside of the well. What that means is the probability of finding the particle anywhere outside the well is 0. Because you have an infinite potential. You don't have enough energy. You're never going to have enough energy. The finite well, though, is not that way. The finite well, when we draw these, the level here is to indicate the energy. So this has a negative energy down here, a higher negative energy, a higher negative energy. All of these energies are below the energy at the top. So using classical physics, what are the odds of the particle getting out of the box in any one of those 3 states? None. Doesn't have enough energy to get out. But if you notice, outside of the box, it's not 0 for the wave function, which means I square that and I have the probability density. The probability of the particle being outside the box is not 0, even though it doesn't have the energy to be there. It's a forbidden thing, but it can happen. Why? Because we say that the particle is delocalized, and there is a certain finite probability that it's out here. Now you notice the probability of being out farther is going to 0. So a way I kind of like to explain this is kind of like water in a pool. You might be able to splash water out of the pool a little, but you're not going to have standing water outside of the pool because it doesn't have enough energy to actually be there. Now, this is not splashing now. It's a different thing. But it's waves, and you have a certain probability of being out here, but the probability of it propagating away is 0. It's just you have some finite probability of it being right outside of the region. Now, if you look at these solutions, you notice that they look a lot alike. Really, the fundamental difference is that this here is more squeezed. This is spread out a little. Really, the fundamental difference. So this here was a good approximation to reality. This here is much more reality. And you can see we'd probably be pretty happy doing this instead of this, although if you look at the energy levels aren't exactly the same spacing either. So the energy levels aren't the same, which is actually, to me, the bigger concern. So we're going to look at this. So here is the fundamental problem, the fundamental statement for the finite well. Now, one thing to note that's different here. This finite well has a width of 2a. So the L that we used before would be equivalent to 2a here. It's important to keep that in mind. Second is because most places are at this potential energy, we define this as a potential energy of 0. And so it's at a negative potential energy when it's inside the box, 0 potential energy outside the box. That's different than when we did the particle in the infinite well. We just said it's 0 here and infinity outside. So that's a fundamental difference. It still has three distinct regions. So if you're going to solve this, you should use the same process we did before. So we found a solution in region 1, a solution in region 2, a solution in region 3. Then we used boundary conditions to relate those solutions. What's different here is that it's not 0 probability of being in region 1. It's not 0 probability in region 3. And we don't have an infinite boundary. And so our second boundary condition is going to come into play. First boundary condition was that the wave function had to be continuous. Second boundary condition, unless we have the infinite boundary, which we've now learned what to do with the delta function problem, except for in that case, we're going to have the first derivative is also continuous. So once again, you look at these solutions and you see, yep, the slope is continuous on that boundary. It doesn't go sharp kink. So we got to do our solution. See, this is a really quick problem. All right, so let's go to where we actually do the solution. So in all the regions, you have the same Schrodinger equation. But in region 1, V in region 1 is equal to 0. And so when we write our Schrodinger equation, minus h bar squared over 2m, second derivative psi, plus v psi, well, we just have that term missing because we're adding 0 psi, is equal to E psi. That equation, we now know very well, must have a solution that's of the form of e to the bx. And so we take the second derivative of that, it's b squared psi, we put it back in, and we find, lo and behold, e plus h bar squared over 2m b squared has to be 0 for us to have a solution. And so, right, so I just plugged this here in there. And then collected terms. I factored out the psi 1. That way I don't have to do a division by something that can be 0. But everywhere the psi is not 0, then the other stuff has to be 0. So this has to, in general, be 0. And so that gives us b is equal to plus or minus square root of minus 2me h bar squared, or plus or minus kappa. Now you look at that and you're like, hey, that's a square root of a minus, right? But the energy is going to be negative here. We're only going to do solutions for negative energy. I'm not going to do solutions for positive energy, but let's talk about the difference so we know why. What would it mean if we had a positive energy? If we have a positive energy, here's positive energy. Yeah, it's going to pass over. It's going to interact with this. You're going to have some reflection, some transmission, but it's not bound. You're not going to have quantized energies, so we're not focusing on that. So we're only looking at this case here, E is less than 0. And so that's why this doesn't have any I in it, because you have minus 2m times a negative value for E. It's a positive. So we have B is plus or minus kappa squared. And then our solution, we're going to have two solutions, one for the positive B, well, positive kappa, one for the negative kappa. And so in this region, there's our solution for region 1. Now, quickly, there, get rid of that so you can't see it. Only one of those terms is going to survive. Why will only one survive? Well, it goes to 0, so what survives? For it to be normalizable, it can't blow up. And psi 1 is in the region where x is going from minus a to minus infinity. At minus infinity, which one of those terms blows up? If x equals minus infinity.
Oh, the minus k kappa x.
Yeah. This one here approaches infinity as x approaches minus infinity, because it's e to the minus negatives to the positive. E to the positive infinity is infinite. And so that means that I'm going to have a is 0 for this to be normalizable. And I can never pronounce a normalizable. I don't know why. I can say normalize. It's the able that messes me up. So we end up with only the b term there. Now I have next region 2, but let's just think about region 3. If we do region 3, what's the difference between region 3 and region 1?
The limits.
Just the limits. And so in this case, you're going to plus x. So you're also going to have only one term survive, but in region 3, it's going to be only, excuse me, that's the one that blows up in region 3. It's going to be the only one with the negative exponent that survives in region 3. So that will be normalizable. So we can already see from regions 1 and 3 that our solution is going to be something that goes like this, where 0 is down there, for the wave function. It's going to be exponentially decaying as we go out. And then we have to find out what's going on in the middle. So that's where region 2 is in the middle. So I did these in numerical order, so I'm going to have region 3 and repeating down lower. It's just more convenient to do the two together since they're fundamentally the same problem. So in region 2, now we're going to have a v that's not 0. So when we put that v in here, right, there's the v, and it's negative v0. And by my picture, I already defined that E is a more positive, even though they're both negative, it's a more positive value than E0, or than V0. So that means that when I take this and I rearrange, so I have, let's see, moved everything over so it's all positive. This here, V0 was a positive number because I said I'm at energy minus V0. Right, that comes back to, I define this potential as minus V0. So V0 is a positive value and the potential energy V is minus V0. So V0 is a positive number that is bigger in magnitude than the negative E. So here I have, here, circled, E plus V0. V0 is positive, E is negative, but V0 is in bigger magnitude. So that means that thing that's circled is positive. That's kind of important because I'm going to now take this thing in parentheses and set it equal to 0. And so I have that when I move to the other side of the equal sign. Then divide everything by h bar squared, multiply everything by 2m. And I have b squared is equal to minus, that thing in parentheses is a positive value, 2m over h bar squared. Square root that, and I have the square root of a negative value. You have to pay attention to what the V0 and E are to make sure you, oh yes, this is going to be square root of a negative. And so that's why we define this here. Notice the minus sign is removed. We define that as L. And then we have plus or minus IL because we had plus or minus for the square root and I because it was the square root of a negative value. So I wrote this two ways. I wrote it with C1 e to the minus ILX plus D1 e to the ILX, or C2 sine LX plus D2 cosine LX. They're equivalent solutions. Before, when I did this, I stuck with this one, right? This time around, I'm going to stick with this one. The reason is because I don't have a nice, easy solution like I had before. So it comes with mathematical experience, or as the case is here, having done it before, knowing which way to go. So here we have region 3 with its outcome. And so here's the solutions we have for each of the regions. Now, before I do anything silly like normalize, I first am going to apply my boundary conditions. I would say it's silly to normalize. My boundary conditions, I might be able to reduce the number of constants. And normalization is only going to give me that last constant. Right? I can't rightly normalize when I have 5 constants hanging out. Actually, here it's 4, but, well, actually, it's 4 constants out front, plus we have 2 different exponent constants. Life is fun, right? So, boundary conditions. The first one, the waves must be continuous. So, psi1 must equal psi2 at A, which gives me, and here I put it in the sinusoidal form. Well, I put it in both forms. I put it in both the sinusoidal and the exponential. But we have B e to the kappa A equals C1 e to the ILA plus D1 e to the minus ILA. So this is a relationship between B, C, and D. And then we have our derivative has to be constant. So I take the derivative of psi1, the derivative of psi2, and the derivative of psi1 is kappa B e to the kappa X. Derivative of psi2 is going to be minus ILC1 e to the minus ILX plus ILD1 e to the ILDX. So I'm going to have something that looks a little more complicated when I do the derivative. So notice I did the derivatives again, doing both of the 2 versions of the psi2 function just so we can see how they play out. And so here is a second relationship between B, C1, and D1. And at this point, what can we do? Not much. We go on to the second boundary. And at the second boundary, we again set the values equal to each other. So we get a relationship now between, the way I did it, I can't omit the sine and cosine there. And likewise, doing the derivatives, we get this. So now we have a total of 4 equations there with B, C, D, F, and L and kappa. That work, mathematically, not so hard. I mean, a little tedious, but not hard. But now it gets a little frustrating. Here I have summarized the equations, and I actually, wow, I did keep them in the sinusoids here. I was pretty sure I hadn't kept them in the sinusoids. I thought I kept them in the, or put the exponentials. So here's the equation summarized where I have reorganized things. And I'm a little worried, did I drop? No, I didn't, because these are ones that don't have the exponentials. So I've reorganized them, but I have the functions as simple as they can be, the ones that were in the boxes, as simplified as they can be. So if I add these 2 equations, then I'm going to have the same exponential for both B and F. And so I have e to the minus kappa at A times B plus F equals, and if you look at the right-hand side, the C terms subtract out. Now, keep in mind, I should have pointed out, I use cosine of minus LA is equal to cosine of plus LA, the fact that it's an even function. And sine of minus L equals minus sine of LA. It's an odd function. So that's why you don't have any negatives in your arguments for sine and cosine. So if I add those 2 together, I get this equation. And then I'm going to subtract those first 2. So I added them to eliminate C. Now I'm going to subtract them to eliminate D. And so I subtract them and I get this equation, eliminating D. So I have relationships between C, F, and B, or D, F, and B. And then do the same 2 jobs with the lower 2 equations to get these equations. So actually, I will put these in red boxes. So these 4 equations are equivalent to the 4 we started with, just combining them differently. We haven't really gotten any new information, but we now are at a place where we can, because we have f minus b in this equation and the upper equation here. And we have c on the other side. So if I divide those two equations, I'm going to be able to have a straight relationship between kappa and a trig function of LA. And similarly, with the d, I could do the same thing. I'd get the same result. So before I do that, I do have something here that I forgot until I looked. Looking at these equations, the 4 equations in the red boxes, I'm going to look at symmetry. Because of the solution's symmetry, you either have a symmetric or an anti-symmetric function. That is, our problem itself is symmetric about the center. And so the only 2 real results I can have is something where it's the opposite looking at the left side versus the right side, or it's identical looking at the left side versus the right side. Those are the only 2 things we can have with that kind of symmetry. So one's an even solution, one's an odd solution. And so for an even solution, then I would have b is equal to f. It's exactly the same on both sides. For the odd solution, I'd have b is equal to minus f. And so this is another case where we're using logic instead of just bludgeoning through. Using the logic to make my life a little easier in the math. And in fact, if b is equal to f, then this equation is 0 is equal to 2c sine LA, which is true only if c is 0 or LA is an integer multiple of pi.
Where were you pointing?
Okay, so for the even case, if b equals f, we have either, so if b is equal to f, then that means you take this equation right here, and you have, if b is equal to f, then that's 0 is equal to 2c sine of LA. For the even solution. And so that can only be true if c equals 0 or LA is equal to n pi. So we get that from one of the equations. Now, if we look at the other equation, or let's look at equation with b plus f. If we look at one with b plus f, then we have something that's rather complicated. And so here are the 2 solutions. Oh, yeah. I do say here, well, C is going to have, it's going to have to be the case that C is 0 because sine is an anti-symmetric function. For symmetric solution, you can't have an anti-symmetric. So the C has to be 0. So that's the one that it had to be. So we did not have this quantization because it had to be C equals 0 for it to be even. So then looking at the other solutions, the 2 with f plus b, since f is equal to b, we're just going to say f plus b is equal to 2b. So that's why there's a 2 on the left side and just a b. And then on the right side, of course, this one here is going to be, this one here, it's going to be 2d cosine LA, and this one here is going to be, this one, 2d sine LA. So those are now conditions that we get from those equations if it's the even case. And the easiest way to solve this bad boy is to divide. Divide, the d's and b's both divide out, and we find a relationship between kappa and L and A. Does that work? And now, how do we solve this thing? It's not easy to solve, is it? I mean, what would we be looking for? Kappa and L both have E in it. E is the thing we'd be looking for, trying to solve for E. But the problem is we have, and so, right, there's E there, E there, and E there. We're going to have E on both sides, one in a trig function and one not. It's not something you can do mathematically. It's called a transcendental equation. There's no analytical solution. You can't pop it in the calculator. The calculator uses some kind of, algorithm to give you the exact value based on traditional math. So instead we go with, well, I do this graphically. You can do it with a spreadsheet. But we say, okay, let's take two sides of the equal sign and plot both of them versus our variable. And when both sides of the equal sign cross, when those lines cross, then what we plotted it against, that must be one of the solutions. And so this here is, and I could go all day and probably not come up with this on my own, but defining the new variable z as LA. So that means that this is going to become tangent of z. And if z is LA, then I'm going to have this side here would be, well, the way it's written, you might expect it to be, let's see, 1 over L is equal to A over Z. You might expect it to be something like this, but we just go ahead and define Z0 as A kappa. And let's see. Yeah. Z0 is A kappa. I think that's right. And so with this definition, then what we have for our equation is, I don't want to go through all this work. It's just painful. All of this here is just simplifying the equations to get to this final relationship. The square root of Z0 over Z, quantity squared minus 1, is equal to tangent of Z. So then we plot tangent of Z. So tangent of Z is first this one. There's Z. Then, wait a minute. Yeah. First this one, then tangent, yeah. Then this, then this. Each one of the blue lines is a tangent of Z graphing. And then we have this function here is I think that's supposed to be green line. And so every time the blue line crosses the green line, that is a solution. And so you go through and you find the values where they cross, and you have, here's the first solution for the even case, here's the second solution for the even case, third solution for the even case. And with the numbers that were chosen for this graph, because you kind of have to choose your numbers, that's it for the even cases. That's the only crossings you have. But then you have the odd solutions. So if you go back and you do the same thing, except for you choose the odds. Actually, do I do the odd solution here? Yeah. So if you go back and choose B equals minus F, by doing the same work, you have a cotangent Z. And so this graph has the cotangent Z's plotted in red. And so your odd solutions now are going to be here, here, and here. Now, interesting outcome. With the finite boundary, there are a finite number of bound states. That is, a finite number of states where you have a negative energy. There's going to be a continuous infinite number of states with a positive total energy, but a finite number of bound states with a negative energy. And we had to find them by using this transcendental equation method. Now, after you do this, now you can normalize it. Yay. And so here's the normalization calculation stuff. I'm done with that. Okay, so what do we get out of that? What we get out of that is first of all, going through the same steps. Right on the test, you can be sure that you're going to have to remember and probably apply at least part of the steps of first, put your energy in your equation and for each of the regions you have. Second, apply your boundary conditions. When you apply your boundary conditions, that should lead you to your quantization values. And then third, normalize. Right? Those are always the beginning steps. So we did those here. We ran into a unique mathematical problem of a transcendental equation. And so now we see how we can solve the transcendental equation. We have two equations. There's no way of mathematically saying they equal to each other and solving. And so we just plot each one of those functions versus the same variable. And when they cross, that must be when it's true. And so that's why I circled all those crosses. Those are the values of z, since that's what we use for our variable, where it was true. And then we took the definition of z to actually go and find the energies. So let me actually go back to this just real quick. So we find, for instance, this value of z. And so once we find that value, so in this graph, it'd be like 7.8. What I do in practice when I'm doing this is I plot them on Excel. I find the region where it's close, and then I zoom in, I make it a function. I have like, some epsilon that I'm going to be increasing, and I set the epsilon smaller, 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 so I can zoom in and get more detail, and replot until I get, something like four digits. And I say that's good enough. But then once I have that z value, then I have to come back to my definition of what z was. So we had defined that z was this. So once I know z, then I can solve for what e is.
You can, yeah, okay, so you kind of skip over finding what L is.
Well, L and kappa are both based on M, H bar, E, and V.
Yeah.
And so, yeah, you put in the meanings of L and kappa so you can solve for E.
Yeah. Right.
So yeah, I don't find specifically what L is.
So is it reasonable that you would ask us to solve a transcendental equation using our graphing calculator
No.
to find the cross?
No.
Just to explain? I mean, what?
Yeah, it would be reasonable to explain,
okay.
but not to have you do it. Just that's a calculator skill at that point. Maybe you're good at the calculator, maybe you're not. I don't want your grade to be on how good you are at the calculator. Oh, well. And then homework problem number 4. Or number 6, four, in 1 minute or less. Obviously, we can't do it in 1 minute, but this is another case where based on the symmetry, you're going to have either an even or an odd solution. And it turns out that with the single well, we only had one energy level available, right? As long as it was in the bound state. Lots, infinite number of not bound. With the double well, it's not going to be just one energy state. So, I have the whole work here so you can go through it, but we're out of time. I won't.
Go over it next class period?
I want to review first.
Okay.
If we have time after, I can go over it, or we can just meet another time to go over it. All right.